use this link. Okay, never mind. At the beginning, let's have an overview of the previous materials. In the previous sessions, I had a very big picture of the blockchain. Some notations like transactions, blocks, blockchain, proof of work, cryptographical hash functions, digital signatures, and the like were introduced very briefly. And I'm sure there are many questions in your mind, okay? But that was a very big picture. That was a very big picture from the course. Now, each term will be discussed in detail. For example, now we start the topic 2. In topic 2, I will introduce the cryptographical hash function and the asymmetric encryption. So today our topic is about cryptographical hash function. However, if you have any question about the previous lectures, please ask at the beginning of the lecture so I can continue after your questions. Is there any question? No? Okay. Since the internet speed is limited, so I don't share my picture, okay? Just let's share the slides. Later I will share this, I will send the slides through the forum or through the LMS. Okay. So we are starting topic 2. In fact, I want to talk about cryptographical hash functions, and after that, asymmetric encryption and decryption. So let's start by parity checking and hashing algorithms. How can we tell that message, a file, a document, or something like that has not been corrupted? Suppose that you are downloading a file from the internet. Okay? Suppose that you are downloading a file from the internet. How error detection can be done? There are many solutions. One of the simplest solution is using parity checking. So let's see what's parity checking. Two kinds of parity checking can be introduced. One is odd, or the second is even. Suppose I will share this and after finishing the session, I will share the PDF, the slide, don't worry. Suppose that my message is a binary string like this, 11100011001. Parity is odd or even depending on the number of ones. For example, in the string above, there are 6 ones, so it has even parity. Because 6 is an even number, and if the number is divided by 2, the remaining must be 0. And for the 6, it's okay. So this message has a parity even. Now we can make a rule. What's my rule? All messages must have an even parity. For example, Alice wants to send the message 1101. The number of ones is 3. It's odd, so 1 bit. Alice must add just 1 bit at the end of the message to make it an even number. So the Alice's message will be 11011. Okay? The main message was 1101. Since the number of ones was 3 and 3 is an odd number, we must add another one, just 1 bit at the end of the message. Now we have a message with even parity. When, suppose that Bob is receiver, okay? When Bob receives 11011, checks the parity, everything is okay, there are 4 ones, so everything is okay, and Bob now can remove the last bit, the last one, so he can access to the main message, which is 1101. Now suppose that Alice wants to send 1001. The number of ones now is 2, and 2 is even. So if she sends the 1001, the problem will be that how Bob can understand that the message was 100, because Bob can consider that the last bit is for parity. Okay, so in fact in this case Alice should send 10010. In fact, Alice must add just 1 bit 0 at the end of the message. So Alice must send 10010. As soon as Bob receives this message, he can simply remove the last bit and the main message is 1001. And the parity is even, so everything is okay. This is one of the simplest way to check that everything is okay with the message, with the file. Okay, one of the oldest approaches. By this approach, you can just detect one error, or at least odd number of errors. For example, if my message is 1001, but in the middle of the process of sending, something wrong was happened and my message was changed to 0011, the parity can't detect such an error. So parity checking can help just finding odd number of errors. It also doesn't tell you where the error is. so you can't correct it. You know, parity checking is one of the simplest approaches. You can find just odd number of errors in a message. Also, you can't correct the error. Okay, so let's start talking about hash functions. What's a hash function? I sent you 3 short videos about hashing in general. If you watched those videos, I think one of the applications of the hash functions is cryptographical hash functions. It means that some hash functions which are used in the cryptographical field. I think now you should be familiar with the topic. However, let's talk generally about hash functions. What's a hash function? H is a hash function. What's the input? The input of a hash function is a file with any length. What's the output? The output is strings of length n. It's called n-bit hash function. So input is any file length, output is a fixed length n. In the case of parity was just a very, very simple example. In the case of parity example, the function hx, its input is a sequence of bits, is a binary representation of a message with any length. So x is a binary string with any length. This h of x is equal to sum of bits mod 2. In fact, the remainder of division, sum of bits by 2. So it's a 1-bit hash function. The output is 0 or 1. Okay? So I started with the parity checking, which is one of the simplest examples of hash functions. The hash functions is searching, but another one which is a totally different application is cryptographical hash function. By cryptographical hash function, we can stop others from tampering our data. For example, we have a contract. We want to prevent others to tamper our contract, to change our contract. So we can simply publish the hash value instead of the main contract. In fact, we can hide our data behind the hash value. And it brings for us the security, one of the important points in the blockchain. Security is a very, very important issue. Suppose someone wants to defraud us, someone wants to change our contract to one more beneficial to them. But if we have published the hash value, or we have calculated the hash value, this will stop them from doing this. How? I will explain. Another important point is collisions. What's collision? If two different data, if two different inputs have the same hash value, if two different data, if two different input has the same hash value, we say it's a collision. For example, as a parity checking, H of 1001 is 0 and H of 0101 0 is also, as you can see, I have two different strings, 1001 and the other is 10110. In both cases, the parity bit is 0. So the output of the hash function is 0 and this is a collision, okay? In cryptographical hash function, it's very, very important that our hash function doesn't have collision. In theory, it's impossible. In theory, it's impossible to have a hash function that takes any input with any size but generates a fixed size output. The input is anything with any size, but the output is a fixed n-bit string, for example. I think it's obvious that in theory it's impossible because your input space is infinite, but the output space is limited. So one of the properties of the hash functions one of the most important properties of the hash function, it should be hard to find two inputs with the same output. In fact, the function must be collision free, but as I said, it's impossible. Another important property is that a small change in the input makes a large change in the output. Why? Because nobody can guess the function. We want to use these hash functions as a secure approach to secure our data. If someone can guess the function, if someone can reverse engineering the hash function, it's not a good function. There is an example here. Our hash function is H, in which the input is a person and the output is its birthday at first, number of day from 1 to 31, and after that number of months from 1 to 12. As you can check this, easily we can see that the input can be any people. There are many people in the world, but output is just 3065. Why? So output is a space with a size 365. Okay? Why? Because the number of days in a year is 365. So it's certainly there's a collision when the number of people grows up, and it's not a good function for cryptography. Another application of this kind of functions, hash functions, is fraud detection. How? Any changes in the data results in a different hash value. So simply we can prevent any tampering our data from the others by the hash function. There is a special kind of hash functions which are called cryptographical hash functions. And these cryptographical hash functions are safe. What does this mean? It means that even though in theory it's possible to find two different data with the same hash value, but in practice, at least till now, nobody can find such two different inputs. Let's see some of the cryptographical hash functions. One of the simplest one is MD2. MD2 is one of the oldest cryptographical hash functions. In the there are many online calculators. Let's just to show you MD2 online calculator. Let me share my screen. Can you see this page? Yes? Just there are many online calculators for different cryptographical hash functions. You can simply search it through Google. Okay, it's just one of them. Okay, let's see. Algorithm is MD2. I give the input my name, just Wahid. Encode. This is the output. This representation format is hexadecimal. Do you know what is hexadecimal? In hexadecimal representation, each letter shows 4 bits. For example, this is the output, okay? This is the output. For example, the first D represents 4 bits. By 4 bits, you can generate numbers from 0 to 15. Okay? So 0 is 0, 1 is 1, 2 is 2, 3 is 3, 9 is 9, but 10 is A, 11 is B, and finally 15 is F. Okay? So 3, 4, 5, 6, 7, 8, 9, 10. How many digits here? 3, 4, 5, 6, 7, 8, 10. 3, 4, 5, 6, 7, 8, 9, 10. 3, 3, 6, 7, 8, 9, 10. 33. 33 multiplied by 4 is equal to 132 bits. So it's 132 bits hash function. Okay. If I change one of the characters, so let's copy, paste it here. Now let me change one of the letters, okay, and encode it again. So see the output here and compare. The new hash function, the new hash value is totally different. I just change one character, but totally different. As I said, these hash functions must have some properties. At first, collision. As I said, in theory, it's possible to find two different data with the same hash value, but it was very, very hard. And by changing very small part of the input, there must be an extra change in the output. But the same size, every hash function, every cryptographical hash function generates a fixed size hash value. As I said, it's 132 bit hash function. It means that every output has the same size and it's 132 bits. Okay? Now, okay, so there are many other algorithms. For example, you can open it, MD4, MD5, SHA-1, prime. This is all the cryptographical hash functions here listed. Okay, so I defined the first coursework for you today. The first coursework is to have a research on a historical research about cryptographical hash function which was broken till now. For example, MD2 was broken. What does it mean? It means that someone found at least two different data with the same value. There are many papers about different cryptographical hash functions that till now were broken. Yeah, all of them are different algorithms. MD2, MD4, MD5, SHA-1, all are different algorithms. Okay? But some of these algorithms were broken. It means that someone found two different data with the same hash value. There are different algorithms, so please make a research, write an essay, 4 or 5 pages, just 4 or 5 pages about this. I will send into the Telegram group I will send the topic of the coursework in the Telegram group and the deadline by which you should return the answer. There are different courseworks in the semester for this course, and all of them will be considered for your finalized mark. Okay, the best algorithm, I don't know which one is the best, but in Bitcoin, this algorithm SHA-256 is using. SHA-256 is using, and till now it's okay. Nobody could break this algorithm till now. I think one of the best algorithm is SHA-256. So there are many cryptographical hash functions. Some of them are very, very old and were broken, but some are alive. This family, I think till now nobody could break them out. Okay, let's back to the slides. That was a very brief introduction to cryptographical hash function. Now we are talking about them in detail. What's the application of cryptographical hash function in blockchain? We want to use them to act as a proof of authenticity for a document of some sort. At least let's talk about different properties about cryptographical hash function to make this work. At first, the cryptographical hash functions must be public and computable. What's mean? It means that anyone should be able to use it. For example, now you saw that I found an online calculator for MD2, SHA-1, and other different cryptographical hash functions. Not only there are many online calculators, but also you can simply find their codes in different languages in the internet. For example, if you search, you can simply find the Python codes of the MD2 algorithm. I will run that, and we can compare it with the online calculators. I mean, everyone, if want, he must can have access to this algorithm, and if he implements the algorithm, all the answers must be the same. Another property is computability. It means that this cryptographical hash function must be effectively computable and deterministic. Computability means that there must be a polynomial time algorithm for computing it. It means that, for example, an algorithm with complexity of O(n) or O(n) to the power 2, something like this. And deterministic means that each time we input a specific string, the output must be the same. For example, if the input is Wahid, for example, each time that I compute its hash function, the output must be the same as something that you can see here in the chat box. Another property is that h is a one-way function. What does it mean? It means that it must be computationally infeasible to find x from h of x. So, how you can find the input by this output? You have the hash value. How you can reverse engineer it and find what was the input string? It's not feasible. So it's an important property because we want to use cryptographical hash functions as a security means. Okay? Another important property is target collision resistant. As I said, in theory, it's not possible to find hash functions without collisions. In theory, it's not possible. But in reality, it must be hard, very hard, to find two different inputs like x and x prime in a way that the output of hx be equal to the output of hx prime. As I said, the hash function in Bitcoin is SHA-256 and the output is 256 lengths. Another property is unrulyness. It means that if you make a small change in the input, it results in a large change. X prime means another different input. You can say one input is x, another input is y, and h of x must be different with h of y. It means that two different values must have different hash values. So another property is if you make a small change in the input, it results in a large change in the output. I think you saw that in my example. I changed one of the characters of Wahid and the output totally changed. It helps that nobody can reverse engineer the hash function and nobody can guess the hash function. As I said, in Bitcoin, the algorithm which is used is SHA-256 and the output is a 256 fixed lengths. Okay? maybe you say 256 bit is not too long, so maybe someday someone can find two different data, two different inputs, but generates the same hash value. Okay? For example, you can say, let's have a table for every input. When we generate its hash value, we write both the input and the output in a table. For the new value, at first, we check the table. If in the previous we have calculated the output, so we use the output from the table. But for the new values, we calculate the new hash value and we add them in the table. If I found two different values in the table with the same hash value, I can say, okay, we have collision. But till now, nobody could find such a thing. Why? Because 256 bit is a very, very large number. It's a very, very large state space. Let's listen and watch a short video about how big is 256 bits. Can you see this? Can you? Okay. Okay, thank you. Let's start.
Oops. An important note, nothing is provably cryptographic hash functions.
He's trying to say that we cannot prove theoretically that there is any cryptographical hash functions without any collision. As I said, it's not possible because in theory we have an infinite space of inputs with a fixed length outputs. But here he's trying to say that 256 is a very, very big number. Please watch.
That history is full of these proven attempts, but what we're using in Bitcoin is called SHA-256, and in fact SHA-256 is actually used twice in Bitcoin. You use it and then you take the result and put in an SHA-256 again, and nobody's been able to find any effective ways of doing all the things we're asking them not to find effective ways of doing. So we think this is, so for now it seems to be working as a cryptographic.
Till now nobody could find two different values with the same hash value with SHA-256.
Hash function. So let me, I said before, the hash function SHA-256 it's quite clear from the name. It's 256. So each hash.
Okay, so it's a 256 bit, the fixed size hash function. The output has 256 bits. It's clear. And as you know, as I said, every hex digit is 4 bits. So 256 bits can be converted to a 64 hex digits.
Is 256 bits long, or frequently we write that as 64 hex digits. I guess digits not the right word, but I don't know what it is. Okay, so it's 64 characters in a string, a 64 length string in hexadecimal. So it's not that long, but there's a lot of numbers that fit in there. Okay, so we'll see that in a minute, but first, here's the idea we're trying to get to. It's not reasonable, it's not realizable as a thing, it's a sort of idea. Suppose we want a 256-bit hash function that is completely cryptographic. Well, what H could do is, if you give H of X, if H of X has been computed at some point, then H of X will tell us what it is easily. It's already a bit of a problem. You can't really do that. It's too big a number, but that would be what an ideal random oracle would do. And if it's not been done yet, it says, okay, this isn't in my table. I haven't got a table. What I'm going to do is I'm going to compute. I'm going to make it up. So what I'm going to do is flip a coin 256 times, and each time I flip a coin, I'm going to write a digit 0 or 1, and then I'll get a new number, and that's now H of X. Now that doesn't mean no other number has ever had those same random zeros and ones, that same coin flips haven't come up before. They may have done, but I have no way of knowing. Okay. It's not related in any way I can find that out. So, as I said, a lot of the security of this just comes from the 256 bits there being a lot of 256-bit words. So the reasons we don't worry about collisions are they're rare because of this, and they're not computable because of all of the properties we've got. So how big is 256 bits? How many words are there? Now remember, as I said, it's only 64 bits, 64 characters long in hexadecimal, right? So it's not that long. You can imagine writing it, right? Well, I'm adapting.
Okay. You can see this link. Some information here are used from this link, as you can watch.
These numbers from this website. Okay, so that's the number of 256-bit words is about 10 to the 168th. So if I was writing the number of 256 words, not one of these 256 words, but the number of them using decimal notation, or using our usual notation, it would take 168 digits. So that's pretty long. Okay, to give you a sense of this, in 2013, and I'd like to find it.
In 2013, all the digital data in the world was about...
Recent result of this. All the data in the world was...
just 27 to the power of 3 bits. 27 to the power of 3 bits.
273 bits. 273, 2 to the 700, sorry, what did I say? 2 to the 73 bits. 2 to the 73 is a lot.
Sorry, I corrected. All the data in the world was 2 to the power of 73. And now compare 2 to the power of 73 with 10 to the power of 100 and... compare 2 to the power 73 with 2 to the power 256.
Less than 2 to the 256, right? If you divide 2 to the 256 by 2 to the 273, you get 2 to the 100 and something. So, it's it's if each of those 2 to the 273 bit.
He's trying to say that all the data, all the digital data in the world is less than, too much less than 2 to the power 256.
It was again 2 to the 273 bits. It would still be, you wouldn't be getting any place near 2 to the 256 bits yet. And that's all the data in the world. There are roughly 10 to the 22 stars.
The number of stars in the universe is roughly 10 to the power of 22. Again, he's trying to show you that how big is the 256 bits. In fact, even though it's a fixed number, but it's very, very, very long.
The universe, look how much bigger 10 to the 168 is to 10 to the 10 to the 22. Again, if you divide 10 to the 168 by 10 to the 22, what you get to 10 to the 140 something. You haven't made a dent in that 10 to the 168 by looking at all the stars in the universe. In fact, all the atoms in the universe, and then stars is 10 to the 82. That's still a lot less than 10 to the 256. And if it turns out, as many people think, that 96% of the universe is dark matter, so let's put in the dark matter as well. What does that get us up to? Well, 96%, that's, what are you doing? You're multiplying by another 20 or something, so you get 10 to the 85. Nothing like 10 to the 256. There are a lot of numbers that can be written as 256 bits. Okay, and I'm leaving you with this YouTube video, which is a really interesting take on how big 2 to the 256 is and why that's useful for cryptocurrencies. And thanks for this.
Okay. If you like, you can watch this YouTube video to know about how big is 256. Okay. Now, let's start programming with Python. I want to implement some simple, very, very simple programs, and I want to work with different cryptographical hash functions. If there is any question, you can ask. Okay. There are many applications. Here in this course, we want to use and we want to be familiar with blockchain, okay? Let me make it. Okay. Today there are many cryptocurrencies like Bitcoin, Shiba, and many others, okay? Without cryptographical hash function, it's not possible. So we can say, for example, one of the application. So you ask what's the benefit? One of the benefit is security of cryptographical hash functions. Yeah, no slide. I know. There is no slide now. That slide was finished. There are different. One another is security. If you use Gmail, and other emails, okay, our email, our password, everything was hashed, and after hashing, our messages, our passwords, our data goes through the internet. There are many benefits. Let's short this part. Without cryptographical hash functions, without them, today internet, I'm sure that didn't work. You can't have any online payment without cryptographical hash functions. There is nothing secure in the internet without cryptographical hash function. Okay? Last week, I asked you to download Python, and I want to implement some simple programs. So if you didn't yet, please search Anaconda, download it, and install Python Anaconda. And after installing, I use Jupyter part. So let's use Jupyter, some brief explanation about the environment. When you run the Jupyter, something like this, an explorer will be open. Okay, this is the result of running Jupyter in my desktop. Okay, here you can new a Python file, and something like this will be shown to you. Here, this part is a place that you can simply write your instructions. For example, I3 print I. To run the program, just press this run button here, as you can see. Now, there is another box you can write the second part of the program, as we say that, okay, this is the first part or the first block, it's the second block. For example, I plus 1, again, print I. This is the second block. To know about the syntax and the semantic of Python, it's something like some parts are similar to Java or C, but it has its own syntax. For example, this is a simple loop for I in range 5. In Python, we don't have begin or end, or open bracket and close bracket, okay? Instead, Python uses indentation. This starts from the colon, okay? All the commands with a tab are considered inside the for loop. So, if I write something like this, print I. This is outside of the loop, so I can run. Sorry, we need a space here. Okay. Inside the loop, we have 0, 1, 2, 3, 4. And outside the loop, we have the last value of the I, which is 4. So this is the Jupyter, this is the Python. If you are not familiar with syntax and semantics of Python, you can simply search and study about that. It's not complex, it's very, very simple language. And if you search MD2 Python codes, you will find this code, this program. I don't want to explain what is this. Who cares? It's not important. Just I found the code, I downloaded the code, I copy and paste the code here, and I want to run the code. If I run, this is MD2, okay? If I run it, the input Wahid, this is the output, okay? So the hash value of Wahid by MD2 algorithm is this string. If you go to this online calculator of MD2 as we saw today, Wahid encode, the output is something like this, okay? If I copy and now compare the output, see, the output of this program is the same as this, and it must be everyone that implement the algorithm must generate the same value. Or if I run again now, a simple change in the input, just adding 1 at the end of the string, we have this output. As you can see, the output is totally different with this one. Okay, in the next session, which I'm trying to record it by tomorrow, I will try show you how use other cryptographical hash functions, especially SHA family, SHA-1, SHA-256. As I said, in not only in Bitcoin, but also in many other cryptocurrencies, SHA-256 is using and has an important role in the security of that cryptocurrencies. So for now, I think it's sufficient.